Okay, good morning, everybody, and welcome to day 4. We've got about 50% of us in here, I think, from next door, but hopefully they'll be encouraged to come in as we close the door. So this morning we have a plenary session with the SWMI and MPS tutorials, which our student moderators will introduce shortly. We have 3 concurrent sessions and then poster sessions later this evening. So just a gentle reminder to please put your posters up if you haven't done so already. And we have a SBCCI Queer Beers event, which we'll introduce at the conclusion of the plenary session. So without any further ado, I'll invite our student moderators for the first talk to come up here and introduce themselves and our first speaker.
Good morning, everyone. I'm Xi Lu from University of Alaska Fairbanks, and you can call me Lucy because my name is exactly Lucy in Chinese. Today we are happy to have Dr. Borovsky from Space Science Institute presenting. Dr. Borovsky received his undergraduate degree in astronomy and mathematics at University of Michigan in 1975. And then received his master and PhD in physics at University of Iowa. He's an AGU fellow and a chief editor for space physics for Frontier Journals. He's also our Dreamshy liaison. His research has covered experimental, theoretical, and computational physics. And now he's focusing on the structures of the solar wind magnetosphere, coupling, and the systems science of the magnetosphere. Let's welcome Dr. Borovsky.
Thanks, and it's interesting to see everybody. It's pretty neat. It's kind of weird. How do I get my talk on here? Oh, good. And do I change slides? Yes. Okay, and I do it by good. There we go. And I forward and backward with those guys. Great. Okay, thanks. Well, I wanted to talk about solar wind magnetosphere coupling, and it's a big field and there's a lot going on in there, and I'm not going to talk about much of it. I'm just going to try to make a beeline through an overview of the sort of the global coupling of the magnetosphere to the solar wind. And so this is what my talk's going to do. I'm going to talk about what do we mean by solar wind magnetosphere coupling. And then number 2, we're going to look at data studies of coupling, where you look at the behavior of the solar wind and compare it with the behavior of the magnetosphere and try to learn how the coupling works. And I'm going to spend most of my time on point 2 here. And I'm going to make the takeaway point from point 2 that when you do these data studyings, interpreting the answer is very difficult. It's almost never clear what the real answer is when you get a result, and we'll see some of that. And I'm going to make a 1-slide comment on using global MHD codes to do solar wind magnetosphere coupling, the good points and the bad points. And then I want to spend a couple of slides on a GEM project that's going on to create a whole magnetosphere index for the behavior of the magnetosphere and how it couples to the solar wind. And then I've got 1 slide on things that are not covered in this talk. So what is coupling? So it says a number of things up here. You can think of it, it's the driving of the magnetosphere by the solar wind, and you wonder a number of things about it. Chiefly, you wonder, how does it work? How does the coupling operate? And then you want to know what controls the driving, what solar wind parameters are important, what kind of time lags there are. And then you'd like to know, for space weather purposes, can you predict the magnetospheric activity if you could predict the solar wind state? So a formal definition of coupling that I've seen a lot of times is the transfer of energy, momentum, and mass from the solar wind into the magnetosphere-ionosphere system. And that's really true. And that it's an accurate description of what coupling is, but it's not a very useful description. A more practical definition is that coupling is the driving of convection in the magnetosphere-ionosphere system by the solar wind, and it's the convection that leads to all kinds of effects: transport and heating of plasmas, aurora, current systems, energization of the radiation belt, auroral kilometric radiation. All kinds of stuff are caused by the convection of the magnetosphere and the ionosphere. And as it points out here, the amount of driving is usually measured by a geomagnetic index. And we'll go back to that. The major mechanism, everybody agrees, for coupling is day-side reconnection between the solar wind plasma and the day-side magnetospheric plasma. And there's a sketch here from Bjorn and Priest about that. So here we have the solar wind with it's in this sketch, a southward IMF, and the IMF is northward in the day-side magnetosphere with the nose here. And when you get southward and northward fields coming together, you've got a good chance of having reconnection occur in the plasmas. And the reconnection connects the magnetized solar wind to the magnetosphere. And as the magnetic field lines of the solar wind get carried downstream and they're caught on the Earth's, in the Earth, they get laid down into the magnetotail, and you build up magnetic flux into the magnetotail. And then eventually you'll get reconnection occurring in the magnetotail. And that'll allow the magnetic field lines with their plasma to circulate, and you'll get a magnetospheric convection that goes from night side to the day side. Now, people believe there's a secondary mechanism, and it certainly is not as strong as the reconnection mechanism, and that's the viscous interaction. And this is a sketch from an Oxford paper in 1964, looking down from the north onto the Earth. And it shows the solar wind blowing downward here. And as the solar wind blows around the Earth, if there's any sort of a viscous interaction, a mixing of momentum and mass from the solar wind plasma into the magnetosphere, then you'll get a tailward circulation on the edge of the magnetospheres, like the low latitude boundary layer. And then eventually that will give you a return circulation back here, so you can drive convection if you have a viscous interaction. And the viscous interaction isn't really understood. And as it says here, things we don't know. We don't know the magnitude of the interaction. Some people say it doesn't exist. You don't know what physical processes are acting to give you a viscosity. Kelvin-Helmholtz roll-ups, which I hope Katariina is going to talk about in the next talk. It might be plasma wave diffusion across the magnetopause. It might be some sort of eddy viscosity from a turbulent magnetosheath that gives you that. And you don't know what variables in the solar wind control the viscous interaction. And actually, you don't really know what ones control reconnection either. So I want to show a bunch of coupling data studies. So we're going to look at the statistical comparisons of the behavior of the magnetosphere with the behavior of the solar wind. And we're going to measure magnetospheric behavior with geomagnetic indices. And these are common indices to use. There's a set of high latitude current measurements: AE index, AL index, AU index, polar cap index, magnetospheric convection indices, the KP index, the new HP index, which is a 30-minute or a 60-minute resolution KP, very nice, midnight boundary index, and then you can look at like ring current plasma pressure indices like DST and whatnot. And there's other indices that measure UL activity, state of the radiation belt, state of the substorm injected electron populations and whatnot. I'm going to skip that. So here's a simple plot of a coupling plot. So plotted vertically is the 1 hour lagged AE index. It's lagged 1 hour from the solar wind measurements versus VBZ of the solar wind speed times the GSM BZ, and I put a minus sign here. And so when VBZ is negative, the IMF is northward. When VBZ is southward, is positive, the IMF is southward. So you get good reconnection when the field is southward, and you can see under a southward field, you're getting good magnetospheric activity here. And under northward IMF, you're getting poor magnetospheric activity. Each black point is 1 hour of data. The blue curve is a 50-point running average of the black points, and red is a linear regression line. So the things to notice, it says over here in green, the northward versus southward. Southward, good driving; northward, poor driving. The offset. Now, some people would say that this offset under northward IMF, where you shouldn't be getting reconnection, that this is the viscous interaction. So this is the magnitude of the viscous interaction, but there's other things that can cause that offset. So it's not clear that that's the viscous interaction. So when we make these plots, we typically do a Pearson linear correlation coefficient. It's 57% for this plot. R squared is the amount of the vertical that is not described by knowing the value of the horizontal. And then 1 minus R core square is sort of the error. So in this case, 67% of the AE index is not described by knowing what VBZ is. Pretty poor. So there's problems when you do these kinds of plots and you try to figure out what the driving of the Earth is by the solar wind. And here's some of the reasons why. Number one, all of the variables of the solar wind are intercorrelated with each other. So one variable might have a really good correlation with the Earth, but it may have nothing to do with driving the Earth. And a classic one is the temperature of the solar wind. The proton temperature of the solar wind is lost when you cross the bow shock and get to the Earth. But the temperature of the solar wind is highly correlated with geomagnetic activity. And it's because the temperature is correlated with the velocity of the solar wind. The magnetic field vector of the solar wind changes constantly. So the north-southness of the magnetic field hitting the Earth changes constantly, and there's persistence to geomagnetic activity. So you may look at one time and say, oh, the field is northward, I shouldn't be getting any sort of activity. But the field could have been southward just a little bit before, and the activity of the Earth hasn't cooled off yet. There's noise in the solar wind data, mostly because we're using L1 monitors, and the solar wind that hits L1 is not the solar wind that hits the Earth. It tends to miss by tens of Earth radii. Geomagnetic indices are imperfect measures of activity in the Earth. They just measure one thing. They don't measure all kinds of stuff. And I won't go into this, but there's really subtle math versus physics reasons why you get good answers versus bad answers. So if you tweak something and your answer improves, it could be because of the mathematics, not because you're getting more accurate physical descriptions of what's going on. Always be careful. So we're going to look at a number of solar wind coupling functions, and these are the ones we'll see. The first one we already saw was VBZ, and that's supposed to represent the dawn-dusk solar wind electric field. And the origin of that coupling function is a guess. People guessed that the electric field of the solar wind drives day-side reconnection. There's the Newell function, which is a really good one. It does a really good job. It's argued to be the delivery of solar wind magnetic flux to the front of the magnetosphere. Its origin is the best fit to date. It's the best fit between solar wind data and magnetospheric data. The quick reconnection function is supposed to represent the reconnection rate at the nose of the magnetosphere, and it's a derived index. G is the reconnection coupled MHD generator driver, and it's another derived index. F is a free stream turbulence effect. It's a turbulent viscosity viscous driver, and it's a derived one. And then finally, later on in the talk, we're going to look at S1. It's a composite driver function of the solar wind, and it's the best fit to the data. So here's some of those plots. There's the upper left is the one we saw already. It's AE as a function of VBZ. And it's got all the points plus a running average, and the other ones just have running averages in here. They don't have all the points. This one is the AL index versus the Newell driver function. And you can see its correlation coefficient is 76%. It's getting pretty good. This is the quick reconnection driver versus the KP index. And we do another even better driver with KP. We do this G plus F, that's the reconnection generator function plus the free stream turbulence viscous function. And we see we get a better answer. We get 78 instead of 69, substantially better. So you can make 1 million of these plots, and I could show you 1 million of them if you want, but I want to make a point about noise in the data. So this is following the work of Newell to make the Newell driver. Now the Newell driver up there is V solar wind to the 4/3 power times the strength of the solar wind magnetic field to the 2/3 power times the sine of the clock angle of the magnetic field as seen by the Earth to the 8/3 power. And so what we do here is we do a Gedanken experiment. So we'll make artificial data sets that have 3 solar wind variables and 1 Earth variable in them, just like the Newell does. Newell matches the 3 variables to like the AE index and fits it. So we're going to do that, and we're going to make artificial data sets. And the true answer is that this is what's going to drive the Earth. Variable 1 to the 4/3, variable 2 to the 2/3, variable 3 to 8/3, looking like Newell with 3 variables. And this is the exact answer of what the AE index is in our fake data. And then we're going to start adding noise to the solar wind variables and do the best fits and see what happens. So this is the A, B, and C value, those exponents, versus the amount of added noise to the solar wind data. And when we have 0 noise, we get the answer that we put in here. But as we add noise to the solar wind variables, the best fit formula to describe the data changes. You don't get the Newell formula anymore when we start adding noise. And so we can go a step further. We know the real solar wind data that Newell used had noise in it. So we can look at adding more noise to the real solar wind data. So in this case, we fit the SWMI AE index vertically, the exponents for that, versus the added noise we're adding to the Omni solar wind data. And when we have 0 noise, we get exponents that are kind of similar to what Newell got. Exponent of 2 for the green, which is this sine function, a little bit bigger than 1 for the A exponent, which was the solar wind speed, and the B exponent is about 2/3, similar to Newell for the magnetic field. And as we add noise, these exponents change. And we add noise in 4 different ways. That's all the different curves. The round curve is we add noise only on the solar wind speed. The triangle curves only on the magnetic field. The square ones only on the sine function of the clock angle. And then the dash curves are we add noise to all 3 variables. But the point is that they change. And so the answer you get, if you could get rid of the noise in the data, would extrapolate backward to the true value of what's driving the Earth by the solar wind. And it'd be nice to be able to remove the noise. And I think the last one I want to mention here is the free stream turbulence effect. It's a viscous interaction, and there's an outstanding question about this, whether it's real. There are 4 groups around the globe that have gotten this result, and they all get a really strong correlation, relationship between the amplitude of turbulence in the solar wind, fluctuation amplitude of the solar wind, versus geomagnetic activity. And here's a plot that shows this. It's a plot of the 1-hour lagged AE index versus the amplitude of fluctuations in the solar wind. This is the vector, this is the RMS variance of the vector divided by the magnetic field strength. So this is the wiggle angle of the magnetic field in the solar wind, the RMS wiggle angle for the wiggles. Okay, so to do this, we take our data set, which is, I don't know, 30 years, 40 years of data or something, and we separate it according to the value of the quick reconnection function. So the dark red curve is when the quick reconnection function is in its lowest 10% of values. The red curve, it's in its second lowest 10% of values, 3rd, 4th, 5th. So this is supposed to be when the quick reconnection function is very low. We shouldn't have much reconnection going on the day side. So this is looking in the absence of reconnection. And then as reconnection turns on stronger and stronger, those curves get lifted up. And you can see a real connection. These are all running averages, by the way, not the spread of points. You can see a real connection between the amplitude of the turbulence and the magnitude of the AE index. It's a real correlation. Question is it correlating because the amplitude of turbulence is acting as a proxy for another real important variable, or is there an effect? And I also should point out that we shut down reconnection by using the quick reconnection function, but that's not exact. That can be an error. We've also, two of the groups have also looked under purely northward and sustained purely northward IMF. And this effect is still there. Simulations. Simulations of coupling can be local or global. Local simulations tend to focus in on something like a piece of the magnetopause and look for Kelvin-Helmholtz roll-ups, transport of momentum across the boundaries. They may look at plasma waves and whatnot. And then they can be global. And the global simulations look at the whole magnetosphere and its reaction to the solar wind. It's very powerful. You need the data analysis and you need the simulations. They both help each other understand things. There's a couple of good points about the global MHD codes in my point of view. You can analyze the reaction of the whole system to the solar wind. All the coupling between stuff is in there and whatnot. And you see all the multiple time scales and time lags are in the codes. They're automatically built in. So you can do stuff you can't do with the data very easily. The bad thing in my point of view is that you get numerical errors at boundaries. When you get a steep boundary in an MHD code, you get high derivative terms that you're solving in your equations besides the ideal MHD equations. And they lead to all kinds of diffusion and whatnot. So you wonder at the magnetopause where you have a steep boundary, is the reconnection rate in the code correct? Are the viscous mechanisms in the code the same as the viscous mechanisms the magnetosphere would have? Are the plasma entry mechanisms at the magnetopause in the codes the same as the entry mechanisms that would operate in the Earth? So you don't know, but in future we look forward to higher Reynolds number, MHD codes, global ones, global hybrid and global Vlasov will be very nice to have. Okay, now I want to talk about a GEM project that we're working on. And it's this whole magnetosphere activity index. So here's a solar wind coupling plot. This is a example whole magnetosphere index, and we call it E1, E for Earth. And here's its accompanying composite solar wind driver, S1, S for solar wind. The light blue points are the 1 hour data. The dark blue curve is a running average, and the red line is a linear regression fit. And you can see how nice this is. The correlation coefficient is 93%. And so 1 minus R squared, 14%. So only 14% of the Earth index is not described by knowing what the solar wind is. So it could be a very powerful tool. Oh, and I want to say also it's robust. And that's something Gianluca and I are working on. If we derive these functions using slow solar wind, they work very accurately for fast solar wind. If we derive them in solar minimum, they work very well in solar maximum. If we derive them for weak activity, they work great for strong activity. So there's some advantages that this is going to have, I think. So here's some advantages, thinking about the global behavior and global reaction of the Earth to the solar wind. This technique accounts for multiple aspects of what's going on in the magnetosphere or ionosphere thermosphere system. We use multiple measures, AE index, KP index. We can put in plasma measurements and whatnot. Composite index follows the behavior of the solar wind more directly, so there's much less errors in predictions of the Earth from a knowledge of the solar wind. The relation of the magnetosphere to the solar wind is linear, whereas individual indices tend to saturate when you drive them hard. This one doesn't saturate, it keeps going linearly. Same fit applies to the solar cycle. And this robustness, so since we can take low activity that we know about, and it works really well for high activity that we can check with, it could be that if we get something like Carrington solar wind, some extremely strong driving solar wind we've never seen before, we may be able to predict what the Earth index does. And here's an example of robustness. This is the data set. So this is the Earth index plotted vertically versus the solar wind driver horizontally. The black points are the 1 hour points, and then the colored curves in here are 5 superstorms from that time era. And you can see how the superstorms behave the same way the ordinary Earth behaves. So this is our NSF GEM project. The goal is to produce a composite magnetospheric index and its driver and deliver it to the community. So number one, make the index E1 and the driver S1 available. And then we want to familiarize these indices. Once we establish which ones we're going to use, we want to look at CME driven storms, high speed stream driven storms, substorms, all kinds of stuff, so that we get a feeling for what these indices do and what storms look like from these indices point of view, and even develop a definition of a storm using E1 instead of DST or something. And this is something Jean-Luc and I are doing. It's weird. We're trying to develop an understanding of why this works so well. It's robust. You don't need very much data to get the right answer and whatnot. And we just don't understand that people in epidemiology use this technique. And they can fit 10 variables with 50 data points and they get the right answer. It's just crazy. Research topics not covered. So I just wrote down a number of them that came to mind, and I wrote down some people that work on these topics that come to mind. Dayside transients, when certain solar wind features hit the bow shock, they kind of light up and rattle the front of the magnetosphere. The L1 monitor deficiencies, the fact that the solar wind hitting L1 is not the solar wind that hits the Earth, and that's probably not a good place to be monitoring from. Polar cap potential saturation. This is a big work from the simulation codes, mostly the global MHD codes. Just driver functions and general coupling. Bob McFerrin, Mike Lockwood, 2 big brains, and driving the radiation belt by the solar wind. A lot of people have looked at that. What in the solar wind controls the loss and the growth of the electron radiation belt in the magnetosphere? Magnetospheric mass loading of dayside reconnection by the magnetosphere's oxygen or the magnetosphere's plasmasphere. Local versus global reconnection control, and this is mostly global simulation codes, and Ray Lopez is the big brain on that. Information theory, transfer entropy to get more cause and effect measurements out of the data studies rather than just using correlations. Mach number effects of the solar wind on the Earth. It changes the flow of the magnetosheath. It changes the shape of the magnetosphere. You get polar cap potential saturation at low Mach number. The effects of noise on the data, there's people working on that. And Nitin is here somewhere. And types of solar wind plasma, different types of solar wind plasma from the different regions of the sun. And the question is did they drive the Earth differently? And Sunday at the Joint GEM Shine workshop, 8:30 to 10 o'clock, there's a session on that. So I want to review what I said. I hope I still have time. I just wanted to look at the basics, and I just wanted to show you all the other stuff that I wasn't talking about. So magnetic reconnection is the main coupling mechanism. We don't really know the solar wind controlling factors for it. Interpretation of solar wind magnetosphere data is tricky, and that's because mostly intercorrelations of the solar wind variables, everything's coupled to everything else, and noise from L1 monitoring in the solar wind data. And the clock angle varies, and there's persistence to what happened in the past time when the clock angle was different and whatnot. The big list I showed on point number 5, it's a rich field of research. There's a lot of stuff to do, a lot of people working on it, multiple problems. So takeaway is, let's get busy on this. And so these are the people I'd like to thank for this talk, and I'd like to thank support from the NSF GEM programs. Thank you.
Thank you, Joe. That was very interesting.
Good.
It was a little bit disappointing, though. You talked about these new indices, but you didn't really give any idea what they were. Can you say a few words about that?
Yeah, there are linear combinations of other indices.
Okay.
And the ones I showed probably were 10 indices versus 10 solar wind variables.
So you just looked for what combinations you could combine that would have the highest correlation?
Yeah,
Is
and
that
we use
what-
something called canonical correlation analysis to do that. It's a matrix. You just solve a matrix equation. It's not iterative or anything. It gives you a solution for what's the best.
Okay, so another question, it may be irrelevant, given your new indices, but with the newer formula, I mean, you can evaluate what the noise is, can't you, based on the data? Can you extrapolate, from your curves to find out what?
Yeah, yes. You could do that. Those are the curves, and you can extrapolate back, but how much noise is in the clock angle, how much noise is in the solar wind. So just this morning, I was coding up the IMP8 data to do the study where the monitor is close to the Earth and there's less noise. Don't know the answer yet. I've finished my Fortran.
Okay, it seemed like you could evaluate, you could really do that.
That's the point of this, yeah.
So Joe, very nice talk. I'd
Oh.
like to get your thoughts though on something you didn't mention, and that's the role of interhemispheric asymmetry.
I don't know anything about it.
Okay.
I know it when we put the tilt of the Earth in as a solar wind variable, which is the angle the solar wind hits the Earth. Canonical correlation analysis likes to know that. You put variables, you give it variables, and if it doesn't want to know it, it won't take it. It'll give it a 0 coefficient. It'll take that one, the tilt of the Earth. So the Earth likes to know about it. Earth activity likes to know what that is.
Yeah, and then I presume that most of your indices are based on northern hemisphere data, right?
Yeah, SME. Well, SME is.
Yeah.
And
Certainly the
northern-
magnetometers.
Yeah, well, and we all know there's a yearly variation with those.
Joe, we also have a question from online from Bill Lotko.
Mhm.
What does E1 tell us about geospace? For example, DST is a measure of ring current intensity. Does E1 have a similar physical interpretation?
No, E1 is kind of like overall system activity. But you can still have DST if you want to know what the ring current is doing. So you can still have KP if you want to know what convection is doing. We're not going to throw those away. But E1 is global activity, I would call it. Now, if you get used to, everybody has a favorite index they use. Like I use KP, and I know Vanya uses DST. And we judge things by that. If you learn to judge things by E1, they're a lot more predictable to the things you're trying to judge. So that's an advantage to it. Thanks, Bill.
Oh, so thank you for the nice talk. I was noticing that the plot you showed early on, the index would first sort of increase linear with the solar wind driving. Then at some point, if you drove things too hard, it looks like things would roll over and saturate.
Yeah.
However, the composite index at the end is linear all the way up. So I was wondering
Right.
if you could comment on that.
We don't know why. That's another thing. It works so well, and we're trying to figure out why does it work so well? Why doesn't it saturate? Now, this saturation is almost always, people say it's because you drive it hard. But the fact is, when you're driving out here, your Mach number of the solar wind is very low, and it could be a low Mach number effect that causes the saturation, not just the strength of driving effect. See, everything's complicated to interpret. Slava.
Yeah, thank you, Joe. Very, very nice talk. You said that this composite index is a linear combination of other indices, right?
Well, with some cheating.
Well, it's okay. My question really is, presumably the weights of these different contributions change somehow dependent on the kind of event you're looking at?
No, as I say, if we derive for slow solar wind, we get the same derivation as for fast solar wind. The coefficients are more or less the same. It's really a robust
the
thing.
contributions of the different indices, do they change?
No, they don't.
They
No,
don't.
no.
So
We pick.
the coefficients are fixed throughout.
Yeah, in here there's a fixed set of coefficients. They give us how to calculate E1 from the index, and it's a fixed set of coefficients that tells us how to calculate S1 from the solar wind variables.
That's very
Yeah, they're
interesting.
fixed.
Thank you.
Hey, Joe, over here.
Oh,
Yeah. So you said that the indices that you're deriving are derived from other indices, right? And
Right. Other measures of the Earth.
Right, sure,
Sometimes we do pressure of the plasma sheet or strength of the radiation belt. Those can go in there also.
Okay, but I guess my question, and it's a question because I don't have really a notion of this, but those indices are derived from things
Right.
that have been kind of pre-grouped, right? So
Right.
you get DST from
Right.
equatorial or near equatorial
Yeah.
magnetic field measurements, and you get KP from these measurements and
Yeah.
so on. But it might be that different groupings of the things that make up those indices have better information in it. You know,
Could be.
Just
Could be. But you know, another thing we could do, but it'd be a big job, is we could take the SME stations and not their indices and run the stations into the CCA and let CCA pick which stations with what weights it wants to use.
because it should also be able to tell you in some sense, and again, I'm not an expert, but it should be able to tell you how many things are going on. Like, so if you put in 500 variables,
Yeah.
and it says, well, actually there's 37 and a half things driving this whole system, sort of thing, right?
Well, you'd look at for which ones had the big coefficients, and typically to get down the number of variables, we put in a lot and then we start throwing out ones with small coefficients and
Okay.
boil it down a little bit better. You get about the same answer when you boil it down.
Thanks.
Hey, Joe. Great talk. Oh, I'm going to stand up. Yeah.
Oh,
sorry.
great. Oh.
So looking at this, I think to Nathan Savadis's work on like regression to the mean, right? So any sort of timing uncertainties between the composite solar wind driver and then the response of the whole magnetosphere index, you would kind of see that manifest as for like extremely strong driving, you're going to probably predict a little bit less a smaller index, right? Or at least that's my understanding.
I think more or less not. And we have done this where we put in variable time lags and we optimize the time lags. And it doesn't make much of a difference what the time lags between the various indices are in the solar wind. It improves it tiny bit, but not much.
Time lags on the scale of like hours?
Scale of hours.
Wow. Okay. Well, I can't argue with the line.
Yeah, it's a wild thing. I mean, it's like, as I say, the epidemiologists can fit 10 variables about smokers, overweight, age, and stuff like that to cause of diseases and stuff. And they'll have like 50 people they'll look at and they'll get an answer. It's just crazy.
That's very interesting. Thank you.
Oh, great. Hey, Mike.
Yeah. Hi, Joe. I'm happy to see that you're promoting canonical correlation analysis, and that I think that this is an underutilized tool for us, and that it can highly complement the machine learning techniques that many of us are adopting as a way to understand relationships between drivers and responses.
And to get into system science with actual numbers, this is one path.
Yeah, more understanding behind it. I think the way you were just describing it. I guess one point of caution is the use of R so much on in our things. And I guess one of the assumptions, or an assumption that's built into R and the interpretation of a percent out of it, is that it's based on a Gaussian spread around a linear fit.
Right.
And so putting a meaning behind the percentages up here is
and this is very non-Gaussian. Actually,
exactly. Thank you.
Both for S and for E, the mean value is 0 and the standard deviation is 1. So this is where almost all the points are. And those guys are way out on the tail.
Hello. I was curious about the amount of noise in the solar wind data and how much is known about it. Is it something that is like always there and like white noise, or does it depend on the solar wind?
Well, most of the noise you'd actually probably call error, and it's because the solar wind has a magnetic structure that's on the order of tens of Earth radii big, and there's major changes across those structures in terms of the clock angle orientations. And the solar wind tends to hit the Earth to the dusk side by many tens of Earth radii. After the streamline that hits the L1 monitor passes the Earth off to the desk side typically. And so you're not really measuring the magnetic structures that are touching the Earth. And it's more error than noise.
Joe, we have a couple more questions from the VGEM participants. First one from Joachim Bjorn. We know or think we know that some dynamic effects are strongly driven by the solar wind and others are not. If we find an index that is perfectly correlated with solar wind, doesn't that just mean that it is based on those effects that are strongly driven?
That's right. That's Joachim, that's right. And in fact, we look at the error in our prediction, and that error goes way up when a substorm occurs. So one of the things that cause the vertical error is with our solar wind information, we don't know how to predict when a substorm will occur, but the substorm accounts for the major vertical error in these plots.
Thank you. And we have another question from Lynn Wilson. I hope this doesn't imply that L1 monitors are bad or that we do not need them, correct?
Oh, they're great for studying the solar wind. I use the solar wind data all the time when I study solar wind structure. But for Earth, L1 monitors you can do better. You want to do something like the old IMP-8, where it had a circular orbit around the Earth, that if you had a set of those and there was typically always one upstream, that would do much better. And you wouldn't have these crazy 1 hour lags that you have to project the data from L1 as it advects to the Earth, and you're projecting the wrong thing anyways, but the projections don't work very well. They don't work well in fast wind.
We have time for one more question. Are we good? I thought I saw one, but maybe not.
Okay. Well, thanks, y'all.
All right, thank you, Joe, and thank you to our student moderators. Okay, so I'll invite our next student moderators up to introduce our MPS speaker.
Hi, I'm Shan Li from Dartmouth College. Dr. Nykyri obtained her master's degree in theoretical physics in University of Helsinki, Finland in 1998. After that, she continued to do a PhD in physics at the University of Alaska, Fairbanks, as well as another master's degree in computational physics. She obtained her doctoral in physics in 2002 and then worked as a postdoctoral research associate at Imperial College London between 2002 and 2006. In 2007, she started as an assistant professor of physics in Embry-Riddle and was tenured and promoted to associate professor in 2010. And to a full professor of physics in 2016. Her major research interests involve understanding the physical mechanism that transferred heat and X-ray plasma in solar wind magnetosphere system. Between 2012 and 2018, she served as a steering committee member of the GEM as a researcher area coordinator for the solar wind magnetosphere interactions research area. Since 2021, she served as vice chair of magnetospheric division for the Committee of Space Research, COSPER.
Hi, everyone. I'm Akhtar Dakani from University of New Hampshire, and I'll help with Q&A for this section.
we have the laser pointer here? Well, first I want to thank the organizers, Kevin Kenneth-Reddy and Jiping Wang for inviting me to give this tutorial. My first GEM meeting was in 2000, and this is my 20th GEM meeting. So it's very nice to be part of the GEM family, and I grew up with the GEM, so it's a great honor for me to present this work that I started as a grad student a long time ago. So in this talk, I will discuss some of the plasma sheet properties, as well as the physical processes in quite detail, that what generates the plasma sheet during the, in particular, during the northward IMF. I will, in particular, focus on the magnetic reconnection and then the Kelvin-Helmholtz instability and the associated secondary processes. So this doesn't work.
If it's not, then this will work.
Okay. Okay, so this plot is showing the plasma sheet properties from Wing et al. So we know that the plasma sheet ions are colder and denser during the periods of northward IMF. And Simon Wing, he used the DMSP data and showed that the when he mapped the DMSP data into the plasma sheet, he found out that at the dawn sector, the plasma sheet is the cold component ions are more abundant, so it's denser here. And then it's also colder. And in the dust sector, there's typically a two-component Maxwellians. So the cold component and hot component ions, there is a separation in the energy space, versus in the dawn sector, they are almost like, occurring at the same level. When we think about when the solar wind leaves the sun, we have adiabatic cooling. These flux tubes are expanding, so the temperatures of the ions and electrons are going down. But when the solar wind encounters planetary obstacles, it's rapidly heated at the shocks and then further in the boundary layers. But the ion to electron temperature ratio, this is from the Jiping Wang's work, you can see that it's actually pretty constant. So that means that somehow the electrons, they know when ions have been heated. So this is very interesting and tells us something about this kind of a cross-scale coupling mechanisms all the way from the ion scales to the electron scales. Somehow, while we have a collisionless plasma, these scales are communicating. And this is a very nice plot by Joe Borovsky when we talk about the specific entropy. Specific entropy is a measure of the non-adiabatic heating. And Joe had here organized the specific entropy content in the space environment in these different regions. And here, these plots here are showing the magnetosheet flanks for the fast solar wind and magnetosheet flanks for the slow solar wind. And when you move into the magnetosphere, you can see that the specific entropy increases by 2 orders of magnitude. Here is a picture from our statistical SAMU model. So we have a method to organize now about all the spacecraft data. Here we have 12 years of THEMIS data organized based on the physical boundaries, the magnetopoles and the bow shock, where we have each 3-minute THEMIS data interval basically binned with respect to the prevailing solar wind condition. And then we calculate for each 3-minute interval using the Shu magnetopoles model, the location of the magnetopoles, and then the 3D, the reaching bow shock model, the location of the bow shock. And then we normalize and calculate, in the each bin, what is the, we can calculate different statistical quantities, like what's the mean of the means or median of the mean values. But we have basically a lot of data, typically about 10,000 data points in each grid, depending on what grid we use. So here we are showing now the specific entropy in the log scale. And here you can see very nicely in the log scale how we have a very much lower specific entropy in the magnetosheet, which is the shock solar wind. And once we move into the magnetosphere, we get this 2 order of magnitude jump here in the specific entropy. So in order to understand these possible dawn-dusk asymmetries, we can now look into the kind of like dawn-dusk symmetric map, taking all of the all of the possible IMF conditions to calculate what's your average density inside the magnetosphere and magnetosheet. And then we normalize that. So we can then ask, okay, if we have a southward IMF or northward IMF, we can then bin each data point based on those solar wind conditions and then normalize that to this dawn dusk symmetric model. So here you can see that when we include all of the data, you can see that we have much denser plasma here in the dawn sector compared to the dusk sector. And when we look at the situation during the northward IMF, you can see there's a dramatic change. We have definitely a lot more denser plasma here in the dawn sector and the day side when compared to the southward IMF. So the interesting question is what generates this asymmetry of the plasma sheet? So one possible mechanism to understand the why we have an asymmetric plasma sheet density and temperature of the cold components is that maybe we have already asymmetry present in the magnetosheet, or it could be some asymmetry of the physical processes at the flank magnetopause, high and low latitude boundary layers, the large diamagnetic cavities that can be created by the high latitude reconnection and low latitude reconnection, or physical mechanisms in the plasma sheet. So we first eliminated the possibility that the magnetosheet would be the source. So statistically, the IMF is in the Parker spiral orientation. So we typically get quasi-parallel shock here in the dawn sector of the Earth's magnetosphere. And then we get all kinds of wave particle interactions, and we get typically more heated plasma here in the dawn sector magnetosheet. However, when we carefully quantify this using 7 years of TMIS data, it's actually only of the order of 15%. So it's inadequate to explain this 30 to 40% plasma sheet asymmetry that Wing et al. Observed. So the next question is, maybe there's asymmetry of the physical processes at the magnetopause. The main processes are magnetic reconnection, and then of course, what Joe discussed, the Kelvin-Helmholtz instability. So magnetic reconnection, of course, operates most effectively when we have a strongly southward IMF. You open up the Earth's magnetic field and kind of like pull the field here and like peeling it like layers of onion to the night side, and then you have a night side reconnection and then convection back to the earthward. Kelvin-Helmholtz instability operates during a variety of conditions. This is now the onset condition derived from the Kantor-Seghard that assumes the infinitely thin boundary. And here you can see that we get Kelvin-Helmholtz when we have a strong velocity shear along the K vector of the instability, and it basically needs to be greater than the magnetic tension, which is now given here on this side. So if the K vector is strongly perpendicular to the background magnetic field, you can see that this side here goes to 0, and you can always get KH forming. So the main thing is that when you have the strongly northward IMF conditions, you can have the same field in both directions, and even the magnetic fields, when you look into the shear flow plane, they can point in the same direction. The KH can twist the magnetic field and produce reconnection, and as the end result, you capture this cold dense magnetosheet material that can then go into the magnetosphere. So the other question is that can the magnetic reconnect itself produce strong non-adiabatic heating? So here is the interesting result from the paper by Ma and Otto, that we're looking into the PET-check type of reconnection. So this is showing the large-scale reconnection structure. Here we have the diffusion region, and then you have here these slow shocks close to the diffusion region. And this is showing now here the compression ratio of the plasma that scales as the plasma beta. Here we have the plasma pressure and the ratio of the specific entropy. This is showing here the plasma beta and then these different ratios here. The main point here is that you only get strong non-adiabatic heating through the magnetic reconnection when you have a plasma beta much less than unity. However, when we look at our statistical SWMI model, how does the plasma beta actually look like? You can see that typically the magnetosheet plasma beta is of the order of unity or greater. So that tells us that the magnetic reconnection itself is unlikely to produce the strong adiabatic heating directly, through the magnetopause processes for moving from the magnetosheet into the magnetosphere. The one possible mechanism is Kelvin-Helmholtz that was named after these two gentlemen, which is basically now driven by any kind of like a velocity shear between the two fluids. In the Earth's magnetosphere, we have a free energy provided by the solar wind flow, which is gets closely to the solar wind speed after the dawn dust terminator. So solar wind comes through the bow shock, gets deaccelerated, then it's very slow here at the subsolar point. But once you go to the flanks, it quickly captures the similar values as in the solar wind. So we have this velocity shear layer, and that starts to drive the Kelvin-Helmholtz instability. So the ordinary fluids, they are always Kelvin-Helmholtz unstable if you have a low viscosity. For example, honey is an example of the high viscous fluid, so it's hard to get Kelvin-Helmholtz in the honey. So in the magnetized plasma, however, the Kelvin-Helmholtz can be stabilized by the magnetic tension or plasma compressibility. So the sweet spot for Kelvin-Helmholtz is that you need to have a solar wind speed about 300 to 600 kilometers per second. If the solar wind velocity is too high, then the compressibility can actually stabilize Kelvin-Helmholtz. But ideally, you want to have this side quite small, so it works great for the strongly northward or strongly southward IMF. Of course, during the strongly southward IMF, we have a subsolar reconnection operating. So then when you look at the satellite data, it's a big mess. So that's why the northward IMF-driven Kelvin-Helmholtz is easier to recognize in the satellite data. So in the same scale, you can either get Kelvin-Helmholtz or magnetic reconnection in the same plane. So if you have the velocity shear greater than the local Alphen speed along the K vector, then you get Kelvin-Helmholtz. On the other hand, if you have the Alphen speed along the K vector greater than the velocity shear, then you get magnetic reconnection. There's been a number of studies done of the Kelvin-Helmholtz. So there's various simulation studies going from the MHD, whole MHD, dew fluid, and dew fluid with electron inertial effects, as well as hybrid and kinetic simulations. And then we have a number of examples of in situ spacecraft observations. To look at the plasma transport of the KH, we have basically two main mechanisms. One is the floppy entry to reconnection of the large scale magnetic islands. And the second one is the diffusive entry, which is created by the thin boundaries, which is produced by the thin boundaries in Kelvin-Helmholtz. So when we first get Kelvin-Helmholtz, and when you get into nonlinear stage, it starts to create these very thin boundaries. And when those boundaries approach the ion inertia scale, then you can get diffusion through these boundaries. The question is, what happens to that plasma? Does it actually stay there in vicinity of that boundary layer, or can it penetrate deeper into the Earth's magnetosphere? So this is the basic mechanism for when we have the floppy entry. So even with the strongly northward fields, when we have magnetic fields along the velocity shear, even in the same direction, the KH can turn the magnetic field and detach these magnetic islands. And with this, we get the diffusion coefficient of the order of 10 to the 9 meters squared per second. That is being computed from this mass entry velocity, where you can take the mass of these islands divided by the time, and then you take the density on the other side and one wavelength. And then when you multiply this with the typical boundary layer thickness, you come up with this diffusion coefficient. And then you can ask yourself a question: with that diffusion coefficient, how long does it take to populate the 10 years hot plasma sheet after the IMF has turned northward? The answer is it takes between about 2 to 5 hours. As an example of the secondary mechanism, we can get also Rayleigh-Taylor forming here in the Kelvin-Helmholtz vortices. So of course, the Rayleigh-Taylor forms when we have usually the gravity between two fluids. So within Kelvin-Helmholtz, although we are far away from the Earth, we can get effective gravity because of the rotational motion. And that can also then decay these vortices. The magnetic field orientation to the shear layer matters. So if the fields are initially anti-parallel, then when the Kelvin-Helmholtz wraps it up, you actually create now different geometries. So now when we can get reconnection in the vortices, but in this case, we don't capture high density magnetic plasma inside the Earth's magnetosphere, but we capture low density plasma into the solar wind side in this case. So this provides mixing, but not really plasma transport. This same situation was observed recently with the MMS 10 years later, where we had, in this case, very strong guide field, and this was driving reconnection, and there's lots of interesting papers coming from that on the secondary processes as well. However, the real nature is three-dimensional, so these magnetic field lines are tied to the northern hemisphere of the Earth and to the southern hemisphere on the other side. So when the Kelvin-Helmholtz starts to operate, it cannot infinitely wrap up and generate this like a really, really long thin boundary, because you get basically magnetic field lines twisting here in the north and in the south. So you have basically two options. Either the Kelvin-Helmholtz becomes stabilized because of the strong magnetic field tension and the curvature, or you decouple the system and you reconnect this entire blob. And this is basically what SWMI has been studying. So he showed that when you include the 3D effects, you get actually diffusion coefficients of the order of 10 to the 10 meters squared per second. The hybrid simulations, they give about 10 to the 9, and then the kinetic simulations give even higher rates. So the question is like, what are the details to quantify this plasma transport? So there is a mixing rate that usually these hybrid and kinetic simulations are using. And then at the same time, we have the plasma transport where you trace the initial boundary. Here's an example of the Nakamura's kinetic simulation that gets the 10 to the 11 meters, 10 to the 11 meters squared per second. And here you see like lots of diffusion happening when you create this thin boundary. The one important point I want to make is that it's very important to not have periodic boundary conditions, because if you have periodic boundary conditions, you can wrap up the boundary and have basically very, very long interaction layer, and you get more diffusion. Whereas in the real system, the 3D mid-latitude reconnection will already operate and reconnect this larger block of the island before getting, that long region. So SWMI then studied this effect. So he did a whole MHD study with the test particles, and then he compared that with the hybrid simulations and quantified the plasma transport using these two methods. The conclusion is that when you have the whole MHD with test particles, the mass transport happens mainly through the reconnection of the larger islands, versus in the hybrid simulations, you have like a patch reconnection, you get many, many smaller islands. So here is the conclusion of the plasma transport rate. There's one caveat. So the quantification of the plasma transport deeper into magnetosphere, this must define a boundary between magnetosheet and magnetosphere based on the magnetic field configuration first. And once you define that initial boundary, then you can go and trace how much plasma actually gets penetrated deeper into the magnetosphere. Okay, next I talk about the heating associated with Kelvin-Helmholtz. So the IMF is mostly in the Parker spiral orientation statistically. So that means that on average, we get into the dusk sector the quasi-perpendicular shock, and on the dawn sector, quasi-parallel shock. Because the magnetic field is now stabilizing here in the dusk sector, we have a slower growth of the Kelvin-Helmholtz in the dusk sector than in the dawn sector. So this has been also observed in the satellite observations. So this is Shiva-Kawosi's statistical study, and my undergraduate student Henry then sorted this with the dawn and dusk IMF and Parker spiral and ortho-Parker spiral orientations. And we found out that during the Parker spiral IMF, we have more Kelvin-Helmholtz events. For northward IMF, we observed actually Kelvin-Helmholtz at the dusk flank more often, and it was observed always for the higher solar wind speeds than at the dawn sector, because we always have that stronger tangential field in the dusk sector because of the draping. So then going back what Joe was talking about, how these different fluctuations might couple into the Earth's magnetosphere. So here I asked the question, how does the fluctuations look like statistically in our SAMU model? So we have more PC4 to PC5 to PC2 scale fluctuations in the dawn sector. Some of these are explained by the foreshock physics, and you can see clearly that effect over there. But once you have these fluctuations, the interesting question is, what does that do for the Kelvin-Helmholtz? So here, if we take the slow solar wind and fast solar wind, you can see that we have a lot more fluctuations for the fast solar wind here in the dawn sector when compared to the dusk sector. So I then studied this effect by putting these fluctuations into the simulations. These are very long scale simulations of the length of the Earth's magnetospheric system. And the key result is that when we have kind of like the resonance frequency driving the magnetopause, we get larger Kelvin-Helmholtz waves. So all the conditions are kept the same, but for the higher frequency, you get smaller Kelvin-Helmholtz waves. But if your frequency of your seed fluctuation is comparable to the frequency of the fastest growing mode, which scales as a boundary layer thickness, then you get larger KH waves. So of course, the space plasmas, they are collisionless. So the question is like, how do we get now these MHD scale Kelvin-Helmholtz waves transfer the energy to the ion scales, electron scales, and then finally, to the electron scales. And so there are a number of various cross-scale processes that can happen. So basically, when we take the MHD scale Kelvin-Helmholtz, we have a majority of the initial energy is in the kinetic energy of the solar wind. And that kinetic energy is then converted to the magnetic energy by the compression of the Kelvin-Helmholtz instability. And then you are getting these very twisted boundaries. And this is kind of like showing a plot how we currently study these cross-scale processes. So we have now great global simulations. Then we have a local whole MHD simulations hybrid, as well as a Vlasov and particle in cell and Vlasov simulations. So all of these simulations, they have their advantages, and to understand what are the major pathways of the energy and the plasma transport. So in this single slide, I wanted to kind of like introduce all of the cross-scale coupling mechanisms that are associated with the Kelvin-Helmholtz. So we can have the MHD scale Kelvin-Helmholtz to create the thin boundaries of the order of the ion inertial length. This can lead into the magnetic reconnection and generation of the ion beams. These ion beams can now then start to drive ion scale waves. The other possibility is that we have now MHD scale KH. You can get mode conversion, kinetic Alphen waves, and you can get stochastic heating and transport through these kinetic Alphen waves. Here is a nice example of by Justin et al., where you have here in this Alphen resonance, you get convergence of the energy into the magnetosphere by the kinetic Alphen waves. The third mechanism is that the MHD scale Kelvin-Helmholtz can create 3D reconnection. And this 3D reconnection, which is the mid-latitude reconnection that looks kind of like a candy wrapper reconnection, this can create ion shell distributions by mixing of the hot magnetospheric plasma and the cold magnetosheet plasma. And those shell distributions that can start to create magnetosonic waves, and these magnetosonic waves can produce about 1 kilo-electron-volt heating. And finally, we have also turbulence, forward and inverse cascade, and wave-wave coupling processes. So here's an example of the work that I did with my PhD student, Tommy Moore. And here we had a Kelvin-Helmholtz forming here in the dawn sector magnetosphere. Wavelength was 36,000 kilometers. And with cluster, we found this ion scale magnetosonic wave inside the KH vortex. So with two spacecraft methods, you can extract the K vector of this wave, and you can construct the experimental dispersion relation. So this is here showing now the K vector and the real frequency normalized to the ion cyclotron frequency. The black line here is showing the MHD dispersion relation for the fast mode waves. And then the asterisks are showing the experimental relation. And we observed the shell distributions during this time. And then we quantified the heating produced by these waves. So we calculated the wave pointing flux doing these magnetosonic wave observations, and we compared that with the heating that you see here in the boundary layer. And we concluded that this integrated pointing flux during the magnetosonic wave observation it accounts for about 22% of all the available energy surplus. After when we take the kinetic energy into solar wind, then portion of that is used by the compression of the plasma and the magnetic field and twisting of the vortices. Then whatever is left over from that, the single wave packet has 20% of that. So and we had just this 2 pairs of spacecraft that observed this. So we were very lucky. It took like 3 months for my PhD student to find this event just by eyeballing lots of high resolution data. Of course, in the real system, we have these wave packets occurring more frequently. We just don't have spacecraft always at the right region to observe them. But basically this boundary layer, it's a huge area around the Earth's magnetopause. So it's really the main surface, which is, assuming that this process is happening most of the time, that's a very, compelling mechanism to produce this about 1 keV heating of the cold solar wind plasma. And how do we generate the shell distribution? Here is the 3D simulation by SWMI, where he traced the magnetic topology of the different boundaries. And then we were looking into how the test particles are moving in these MHD fields. And the test particle simulations found, we were discovering this, I call it the cat face distribution. So this was also seen by the Taylor and Labrod in 2007 in the cluster data. And then we found also the shell-like distributions in this turquoise region here, which is the double reconnected magnetospheric flux. So this 3D reconnection in Kelvin-Helmholtz vortices can produce these ion velocity distribution functions that then have free energy to drive these kinetic scale waves. So with MMS, it's wonderful. We have now lots of observations in the yet unexplored regions of the magnetosphere. So MMS goes also to the high latitude region. And this is an example where we actually observed Kelvin-Helmholtz here close to the exterior southern cusp. You see these wavy signatures over there. And the point I want to make with this is that here we have now high energy particles. This is showing the from the Phoebs instrument, the 70 to 600 keV electrons, and this is showing the ions. And then these are showing the low energy particles. So when we look at the electrons, we see these high energy electrons that are kind of like strongly trapped here in these vortex structures versus the low energy electrons, those are counter streaming. So what we want to understand better is that what is the interaction between these large-scale diamagnetic cavities that are created by the high latitude reconnection that can actually trap and energize particles to hundreds of keV, namely in the dust sector and dawn sector of the northern and southern cusp. You can have also simultaneously Kelvin-Helmholtz forming. So depending on the prehistory of the IMF, you can have a situation where you have created these pockets of these high energy particles in the high latitude boundary layer. And if you now switch on the Kelvin-Helmholtz there at the same time, it could basically now open up that magnetic bottle and it would maybe transport those energetic particles deeper down to the magnetotail or release them in the magnetosheet. Or one possibility is that are these particles locally accelerated? Here is just an example of my recent paper of this diamagnetic cavity generation. So this is a typical signature. We see a strong dip in the magnetic field strength. We have a trapped high energy electrons and protons. Because the protons are less adiabatic, you can see that they can leak out more easily from this bottle structure. And regarding the mass loading of the magnetosphere, what is very interesting is that we also see their energized O+. So we actually get this outflow of the cold ionospheric O+ into these cavities. Those O+ ions are trapped, they are accelerated, and then they can leak out. And of course, they carry a major mass, and they can themselves affect the Alfvén speed, and then also the reconnection and the other processes that follow. We also looked into what generates the heating of the low energy electrons to up to few hundred eV. So in these regions where we have the boundary now wrapped up by the Kelvin-Helmholtz vortex, we get the very, very strong gradients here in the local Alfvén speed. So we can create, we found their kinetic Alfvén waves by again using this same multi-spacecraft technique that we did with the Tommy's work with the cluster. So we were able to pull out the dispersion relation and show that this was a kinetic Alfvén wave. So I then quantified the heating produced by these kinetic Alfvén waves, and I concluded that it wasn't sufficient to produce all of this heating. So there is still some unknown physics that we don't quite understand. So the unknown physics could be magnetosonic Whistle branch waves, or we also need to quantify the contribution from the parallel electric fields created by this mid-latitude candy wrapper reconnection. Finally, this is a nice paper by Sarati et al. That looked simultaneously the transport and the properties of the entering plasma from the cusp reconnection and from the Kelvin-Helmholtz. The main conclusion is that the combined flank and cusp entering solar wind ions, it can recreate this observed two-component hot and cold dusk and broad peak dawn population at tail flanks. So basically the entering plasma, it has some different properties. So the previous works have showed that, of course, when we have the double high latitude reconnection in the northern and southern cusps, you can basically create this big gold dense flux tube. And Taylor et al. We were comparing the phase space densities using the double star spacecraft, and it showed that high latitude reconnection is very effective in generating gold dense plasma sheet closer to the Earth, but it doesn't explain it like when you go to the further down distances. So that study concluded that the Kelvin-Helmholtz is definitely more important when we go further down the tail, but the cusp reconnection is also important when we are closer to the Earth. But the energization in the cusp and energization through Kelvin-Helmholtz, that will then give us this detailed structure that we see in the energy spectrograms in the dawn and dusk sector flanks of the magnetosphere. Okay, and I will conclude. So I believe that we have done some progress during the last 20 years since I started to work on this topic as a graduate student. And I think we pretty well understand now how the plasma gets transported into the plasma sheet during the northward IMF. So I think the great detail of the plasma transport, in my opinion, has been solved. So these are the open questions that I think are now interesting to pursue. Can the Kelvin-Helmholtz locally accelerate hundreds of keV electrons and protons? What is the cross-scale mechanism to create the 200 eV counter-streaming electrons within Kelvin-Helmholtz vortices? What is the mutual interaction between diamagnetic cavities and Kelvin-Helmholtz? Which of the following are the dominant source of the inner magnetospheric ULF waves? The high-speed jets, solar wind pressure pulses, or Kelvin-Helmholtz waves? And finally, how do these Kelvin-Helmholtz signatures map into the ionosphere, both for the optical signatures and then to the ground magnetometer signatures? Thank you.
Questions?
Thank you, Katariina. In one of the early slides, you showed the distribution of the specific entropy, but I noticed there's a blank right on the left side. What causes that?
This one?
Right.
So what's this one? So we have the very strong magnetic field here. So then the specific entropy, it's a function of the plasma density and temperature. So we have a very cold plasma here closer to the Earth.
Oh, it's just near that x equal to 0 line on the night side that look like the heart.
Oh yes.
Night side, sorry. I mean the night side.
Here?
Yeah, there's that
Yep.
sharp peak. No, near the Earth. I'm not sure if that's caused by orbit or no. On the night side of the Earth, close to, yeah, there.
Oh, yeah, I don't think we have data from that region. So there's like some artifacts, yes.
Hi, Katariina. That was a fascinating overview of stuff. I was interested by the stuff you were talking about the seed fluctuations and how the Kelvin-Helmholtz kind of picks those out and picks out the associated frequency. So could you clarify, were you using purely like narrow band fluctuations for this? And then if that was the case, I'm interested, what happens if you put a turbulent spectrum in? Does it still do that? Does it still pick out the dominant frequency, or do you get really quite a broad excitation?
That's an excellent question. And I did both. So I studied the singular frequencies with the 2 different amplitudes, and then I did the broadband spectrum. So when you include the broadband spectrum, like all of the frequencies from including the high frequency going to the low frequencies, then the results are almost identical. So the broadband, it doesn't change if you keep all the other plasma parameters the same. So the thing where this can actually then play a role, if we have now some, a solar wind driver that has a characteristic frequency, for example, a CME and the CME sheet regions. If those sheet regions have mostly low frequency fluctuations and those get transmitted through the bow shock, then I believe we can have a larger scale Kelvin-Helmholtz waves, and then those can then excite larger ULF waves and then interact more effectively with the outer radiation belt particles.
Hi, Katariina, over here. The magnetosheath tends to have a core halo proton distribution, and the hot plasma sheet in the magnetotail has a core halo proton distribution. When you capture under northward IMF, do the protons have a core halo distribution in the magnetosphere again?
So with our statistical SWMI model, we haven't separated the cold component from the hot component. So we have just a whole ESA distribution which measures up to 30 kV. So we are in the process of doing that next. So we haven't completed that study yet.
Any more questions?
Thank you. Another slide, you showed the relative strength of the velocity shear and the Alfvén speed, which determine whether it's KH or the reconnection. So is there any evolution pattern about the relative strength of these two speeds?
So you mean this one?
Yes.
Yeah, so this was initially studied by Jen et al. In Alaska. And when you have very, very strong current layer, you can get reconnection occurring first because the Alfvén speed is much higher. But then when you start to put on the shear flow, basically what happens is that the information that reconnection is propagating is trying to propagate away with the Alfvén speed. But when the strong shear flow is going this way, it kind of prevents that from happening. So that's and there is the it depends also really on what is your initial strength of this current layer. So the early works, they talk something about the vortex induced reconnection that is slightly different, because then you already at those points had a very strong current layer to begin with, and then but it's not really Kelvin-Helmholtz driven reconnection in those cases. But this is the main characterization. So you're basically comparing the velocity shear strength relation to the jump of this Alfvén speed over the boundary along the K vector. Here's one person. Oh, yes, she was first.
Because I'm right here. So thank you. As a MI coupling scientist, I would like to know what kind of impact this Kelvin-Helmholtz waves and instability would impact the ionosphere. And do you have some insights on that? I would like to hear.
Yes, I had a master's student who made a thesis of that. So we have a paper published on this. So what basically happens is that when you have the Kelvin-Helmholtz waves forming in the flanks, for a certain period of time before the wave is not too far from the Earth, you have a finite time when the Alfvén waves from the Kelvin-Helmholtz are propagating along the magnetic field into the ionosphere. And then you will see an ionospheric footprint. So, so basically there is these auroral spots. You can create these bright spots of the aurora. And if you do kind of like the magnetic flux conservation, you can kind of like estimate what's the size of the vortex, and then you can know what's the magnetic field strength at the low latitude boundary layer. When you map that flux into the ionosphere, it scales up exactly with the observed bright spots. The other phenomena are the ionospheric vortices, the traveling convection vortices. You usually see them like maybe 1 or 2 in the radar. They propagate tailward and then they disappear. And that is because now when the Kelvin-Helmholtz moves further down the tail, then the alpha speed propagation time becomes too long, and then it doesn't anymore communicate with the ionosphere. If you want to hear more, Jay Johnson has and is working with Shiva Kavosi and Simon Wing on the interesting project. There is actually kind of like a magic size of the vortex that produces the strongest ionospheric signature. So I can send you the paper of that.
I just wondering, can you comment on if the KH is still important during the southward IMF?
Yes, so during the southward IMF, we have a reconnection operating mostly at the subsolar point. And then when you go a little bit away from the subsolar point, when you start to create the velocity shear, what happens is that the Kelvin-Helmholtz can actually modify the reconnection rate. So SWMI has 2 papers on this, depending on which starts as a primary mechanism, whether you start magnetic reconnection, the 3D as a primary mechanism, or whether you start Kelvin-Helmholtz as a primary mechanism. So this cartoon here only applies for the Kelvin-Helmholtz and reconnection in the same plane. However, in the 3 dimensions, they can both occur simultaneously. So an example of that is exactly the reconnection during the southward IMF. So we get the anti-parallel magnetic fields, you get the reconnection, but then the shear flow, and then when Kelvin-Helmholtz starts to twist that, you actually enhancing the reconnection rate. So therefore, it's very important to really, I think, take into account in this maximum shear model and the other kind of like empirical models when we try to think about where do we have anti-parallel reconnection forming at the dayside magnetosphere. We need to take into account the shear flow as well to have more realistic estimations where the reconnection actually happens.
So no more questions? Oh, okay.
So I do have a follow-up question about my question just before. Should I worry a lot about the Kelvin-Helmholtz wave when I do the ionospheric science? What is the impact? Is it huge, so we should always consider, or yes?
Well, I think we can estimate what's the polar cap potential drop produced by the Kelvin-Helmholtz. I think my estimation, it's about 30 kV. So to that extent, I think it's quite, because it happens most of the time, all the time. So it gives that kind of like a background convection all the time into the ionosphere. But it depends also a lot about the kind of like the history of the IMF and magnetosphere, how this MI coupling works. So I think it depends on what has been the previous state as well. So
so you are thinking of some viscosity kind of interaction, and so that 30 kilovolts is probably the contribution of this.
Yes.
Yeah. Okay, thank you.
And of course, in the ionosphere itself, the Kelvin-Helmholtz is an important process, also produced like a local mechanism. So that's then different. So both the low latitude boundary layer Kelvin-Helmholtz can produce ionospheric signatures, the high latitude Kelvin-Helmholtz can produce ionospheric signatures, and locally generated Kelvin-Helmholtz in the ionosphere can produce ionospheric signatures. So the reality is somewhat the combination of those 3.
But you also said that they could create the bright aurora spots, right? And then how strong is this? And the size of it?
So the bright spots are usually about 100 to 200 kilometers.
Okay.
And the brightness, I don't remember the quantity from the top of my head. I used the polar EUV image. I have the number in my thesis.
Okay, yeah, I will check. Thank you.
Over here, Katariina, on your left.
Oh, hi.
So 2 quick questions. One is, could these be related to, or are these related to the poleward moving auroral forms that people look at in the like Svalbard imaging near around like when you have noon in darkness on Svalbard, for instance?
So I think there could be multiple processes contributing to those. I think one of my recent favorites are these magnetosheet jets that also occur, very, very frequently. And those magnetosheet jets, they can produce transient dayside reconnection. And when that flux tube is the field line is connected to the other side to the solar wind. So when that gets transported over the polar cap to the night side, I think that could also be linked to those signatures. But I don't know for sure yet. Maybe usually there is, combination of these mechanisms. So Kelvin-Helmholtz could also be producing some of those.
Okay, and the other point is like, and Hyunju just touched on this, but in the previous tutorial, Joe was talking about looking at, whether the viscous connection has a baseline, contribution to the cross-polar cap potential. And is there a way to quantitatively explore that with the modeling that you're doing to look at, because Joe is like, is it there or is it not there when he showed that? Because is there other things that could give you that baseline cross-polar cap potential? And is there a way to resolve that with these simulations?
I think the advantage of the current global 3D MHD simulations and the fact that to be able to resolve Kelvin-Helmholtz, you need to have a numerical diffusion less than 10 to the 9 meters squared per second. The cool thing about that is that you can artificially kill Kelvin-Helmholtz. And then you can calculate, you can measure what the polar cap potential is. And then you can put the Kelvin-Helmholtz in your code and then measure it afterwards and then extract the truth. That's how I would do that.
Okay, here are the comments regarding to your polar motion auroras and the Kelvin-Helmholtz instability. I think it's possible because the polar aurora, sometimes people talk about this low latitude reconnection, but when wrong latitude reconnection happens, it's reconnect the magnetic field into the Earth world. So the aurora signature move in the total way instead of the forward. Well, Kelvin-Helmholtz can operate in the high latitude, and it happens when the solar wind is down dusk domains. And that in that case, it's less stabilized. When the solar wind is down dusk orientations, it can happen reconnection at the top. So in that case, it's with general reconnecting signature. At the same time, the KHR will conversion to a tailward. So it's more like, may looks like a aurora signature move to the poleward. So I think that's likely the case. And we have a paper about that. It's published in 2016-ish.
Okay, any more questions?
Hi, Katariina. We have one from online from Bill Lotko.
Okay.
Katariina, any thoughts on the effects of ionospheric drag due to finite conductance on Kelvin-Helmholtz instability and its nonlinear evolution?
Finite ionospheric drag. So I think that ties, you mean Kelvin-Helmholtz on the low latitude Kelvin-Helmholtz, on the high latitude Kelvin-Helmholtz?
He doesn't specify in his question.
Okay, well, the line tying into the ionosphere, that will definitely help stabilize the Kelvin-Helmholtz. So there's the typical wavelength that it needs to be sufficiently large wavelength to be able to create KH because of the field line curvature. And so the ionospheric conditions and oxygen outflow, when you damp or when you put that heavier, for example, O+ outflow into the ionosphere, that will now affect the local Alfvén speed. If those get further, if that mass gets further into the location where the Kelvin-Helmholtz is forming, that can affect the growth rate of that. So actually, Brian Walsh had a paper on looking into the effects of the plasmaspheric plume when you take kind of like the cold and dense plume and then look that with the Kelvin-Helmholtz. So it actually can increase sometimes the growth rate, because then you can actually reduce you will reduce the density asymmetry over the boundary, because the density asymmetry over the boundary where Kelvin-Helmholtz is operating, that can also act as a stabilizing effect. But if we just look into the ionospheric conditions, unless that ionospheric plasma then comes further down, or I don't know how it would directly from the ionosphere affect the low latitude Kelvin-Helmholtz, because the distance is so big. But once you get that ionospheric plasma out to the region where the wave starts to grow, then it will have an impact. Any other questions?
Yeah, I thought someone had questions from there. Okay. No more questions?
Yeah, the issue of the viscous interaction has come up several times. And if you run global MHD codes with 0 IMF, you get a residual potential, 20 to 30 kilovolts and some, weak region 1 type current. And if you look into the code, you see that the low latitude boundary layer is entrained by the solar wind flow. We assume it's Kelvin-Helmholtz, but we don't know for sure. But that's the general assumption when you look at these MHD codes. So yeah, there is a viscous potential in the MHD codes. When you run it with 0 IMF, there's still convection.
Yeah. So I think you so to really resolve the Kelvin-Helmholtz, you want to have a numerical resolution, at least about 5 grid points per physical length scale you want to resolve. So for the Kelvin-Helmholtz, the critical length scale is the thickness of the initial boundary. So the global MHD codes, the best way to get the Kelvin-Helmholtz to show is that you initially run your code with the southward IMF. So you create kind of like a thin boundary because of the subsolar reconnection. And then when you turn it northward, then you have that brief moment when the boundary layer is still kind of like thin enough, and then you can create more easily the KH waves. But you have to, at that point, when you have the southward IMF, you take that boundary layer thickness and you need to have at least about 10 grid points for that length scale. So, and then to get to the kind of like the details to resolve the reconnection in the vortices, you need to get to the resolution of about 40 kilometers. Will?
Yeah, I just wanted to bring up something from the distant past that in the 80s, John Wygant did a study, I believe it was based on balloon-borne electric field measurements, where he looked at cases where the IMF had been northward for many hours. And of course, what he found was there was sort of an exponential decrease depending on how long the IMF had been northward, but it saturated at about 10% of the value of the cross-polar cap potential for southward IMF. So that was interpreted as the effect of the viscous interaction.
Yes, and actually you bring up a very important point, like, again, going back to what is the pre-state of the IMF. So if we keep the IMF going northward a long period of time, then you are creating a thick boundary layer already in the day side. So that boundary layer after 30 minutes of the northward IMF cannot anymore seed a short wavelength Kelvin-Helmholtz mode, but it has to be thicker. Have to be a longer wavelength mode. And then you would start to see then those rolling up at the lunar orbit. So I think Chi-Ping Wang has some nice observations from the Artemis data at the lunar orbit. But that's a very interesting point, because you always have to think about the kind of like a history of the IMF and what's the history of the boundary layer thickness. And then you can kind of like think about what's the ideal wavelength of the Kelvin-Helmholtz mode.
Any more comments or questions? So let's thank Katariina one more time.
Okay, let's thank both our speakers and our student moderators as well. Okay, so now we have our last item, which is some announcements. So we'll start with our student reps and then move on to our focus group leaders.
Okay, thank you. Good morning, everyone. So we have two important announcements. We have our student rep elections happening now. We have 3 candidates. We have Dominique Stumbaugh, we have Shinju Chen, and we have Hector Salinas. So we have 3 great candidates. Voting is open for students until tomorrow at 7, and then we'll announce our candidate after the plenary tomorrow. The poster competition is underway. We have our Tuesday done. Thank you to every judge who volunteered. We're really, really grateful. The students will be very, very happy with having feedback on their posters. We do need you to check in with us. If you're judging a Thursday poster, we need you to come in and let us know that you're here because we've had some confusion with judges doing the wrong poster or inputting interesting information into the form. So we have to make sure that we're all on the same page for that. So please do check in with us. And students, please stand by your posters. If you're not by your poster and the judge can't find you, you're not going to be judged. So just keep that in mind. Thank you.
So tonight, after the poster session at 30 p.m., we will have a Queer Beers. It's hosted by Yvonne Tyler. Where is it? Oh, do you want to come over and say a few words?
Hello. Yeah, I'm not so much hosting as I just said, hey, let's do this. But yeah, we're gonna have our yearly Queer Beers in person again this evening after the poster session between, what is it, 8 and 8:30 and about 10:30. I think we have it reserved till. So it'll be on the 5th floor, like the pool deck area. There's like a separate deck there that we have reserved for it. So you can get drinks at the bar if you wish to, or not get drinks at the bar, whatever. And then we'll have some time to hang out. This is open. This is sort of our celebration of our queer members of the community, but anyone is welcome to come. Anyone who wants to hang out with us, the more the merrier. So please feel free to join us tonight.
Hi, everyone. In this room, right after the break, we will have the interhemispheric asymmetries and the CDAR joint session on polar cap patches, followed by...
Everyone, also in this room after lunch, starting at 1:30, we will have a joint session between MPIC and IMIT. We'll talk about the precipitation and the coupling between manosphere and ionosphere.
Which will then followed by in the same room with the joint session between interhemispheric asymmetries and IEMIT focus groups.
Hello, everyone. Our reconnection focus group will have one more session this afternoon at 3:30 p.m. in the Bluefin room. Today's focus will be the local reconnection physics. Thank you.
Hi, everyone. Hope you don't mind this little longer explanation, but so models have shown that BBFs, DFBs, and mesoscale injections are important for both ring current and radiation belt buildup, but it remains difficult to verify with observations, and therefore the exact role remains an open question. Model results are inconclusive because existing models do not describe all the relevant domains self-consistently while capturing the required range of spatio-temporal scales. In our next session at 10:30, the dipolarization focus group therefore asks, how is plasma and electromagnetic energy transported through the plasma sheet to the inner magnetosphere at different spatio-temporal scales? So especially with the decadal survey coming up, we're going to be discussing a white paper that's been coming out of our focus group. We welcome you to talk about any white papers you might be bringing up. And we have a few presenters who responded to the questions we posed in advance in GEM Messenger, which are, what do we currently know from models? What are the limitations of the current models? What modeling advances are required and feasible to resolve these limitations in the near and long-term future? And what do we currently know from observations? What can we still learn from existing observations? What are their limitations? And what new observations are required and feasible to resolve these limitations in the future? So we plan to have a discussion. Like I mentioned, we have some people who prepared a few slides to kick off the discussions, but we welcome you to come and share your thoughts. We'd love to hear from you. So that'll be 10:30 in the Bluefin room. That's the 3rd floor. Thanks.
Okay, so the cold plasma focus group will have two sessions, the last two sessions in the afternoon. The first one is on recent technical progress, and it will be kicked off by Alex Glosser with the synsetting talk. And the last session will be on white papers for the decadal service. We have a few panelists that will discuss some ongoing efforts in this direction, and any other white paper or idea that you might have is actually, we will be happy to discuss. So thank you. See you in the afternoon.
Okay, so that concludes our morning session. Let's go to an early break.